Welcome to this video on the dot product. I'm going to explain its definition and demonstrate its calculation. I'll show how we can use the dot product to calculate the angle between two vectors. I'll also show how we can use it to test whether two vectors are perpendicular. If you're looking for information about only one specific topic, please use the timestamps in the description below to skip ahead to that part of the video. The dot product u dot v of two vectors u equals u1, u2 and v equals v1, v2 is equal to u1, v1 plus u2, v2. To explain this, we refer to the dot product of the vectors u and v as u dot v. This highlighted in red is the component form of the vector u. u1 is the horizontal component of the vector u, and u2 is the vertical component of the vector u. For the vector u in the diagram shown to the right, the horizontal component u1 is equal to 2, and the vertical component u2 is equal to 4. So for this vector u, we have u equals u1, u2 is equal to 2, 4. This is the component form of the vector v. v1 is the horizontal component of the vector v, and v2 is the vertical component of the vector v. For the vector v in the diagram shown to the right, v1 is equal to 3, and v2 is equal to 1. So for this vector v, we have v equals v1, v2 is equal to 3, 1. We can calculate the dot product of these two vectors u and v by substituting the values of u1, u2, v1, and v2 into this equation. We have that u1 is equal to 2, v1 is equal to 3, u2 is equal to 4, and v2 is equal to 1. 2 multiplied by 3 is 6. 4 multiplied by 1 is 4. And 6 plus 4 is 10. So we've just calculated that the dot product of the vectors u and v is equal to 10. The dot product results in a scalar value, not a vector. The dot product is also referred to as the scalar product or inner product. We can use the dot product of two non-zero vectors to calculate the angle between those two vectors. The zero vector is the vector with all components equal to 0. A non-zero vector is any vector which is not the zero vector. The angle theta between two non-zero vectors u and v is equal to the arc cosine of u1, v1 plus u2, v2 divided by the length of the vector u multiplied by the length of the vector v. I'll explain this equation now. This equation is a consequence of the law of cosines. I'll derive this equation at the end of this video. This function now highlighted is the arc cosine function. It's also referred to as the inverse cosine function, written as cos to the power of -1. To explain this, when we have that the cosine of the angle theta is equal to this value, now highlighted in red, then we can calculate that the angle theta is equal to the inverse cosine of that value. In this video, I'll be referring to the inverse cosine function as the arc cosine function. This is just a different name for the same function. u1 v1 plus u2 v2 is the dot product of the vectors u and v, which we can express as u dot v. The vector u between a pair of vertical lines represents the length of the vector u. This is also referred to as the magnitude of the vector u. The vector v between a pair of vertical lines represents the length or magnitude of the vector v. I'll now calculate the angle between the vectors u and v shown to the right. Earlier in this video, I calculated that the dot product of these two vectors, u dot v, is equal to 10. I'll now calculate the length of the vector u. Because this vector's initial point is at the origin, the point 0, 0, we can calculate its length in the following way. It's equal to the square root of u1 squared plus u2 squared. Here, u1 is the horizontal component of the vector u, which is equal to 2, and u2 is the vertical component of the vector u, which is equal to 4. Substituting these values in, we have the square root of 2 squared plus 4 squared. 2 squared is equal to 4, 4 squared is equal to 16, and 4 plus 16 is equal to 20. So we've calculated that the length of the vector u is equal to the square root of 20. If this vector's initial point was not the origin, then we would have calculated its length using the formula for the distance between 2 points. We would have calculated the distance between the vector's initial point and terminal points. The length of the vector v is equal to the square root of v1 squared plus v2 squared. This is equal to the square root of 3 squared plus 1 squared. 3 squared is equal to 9, 1 squared is equal to 1, and 9 plus 1 is equal to 10. So we've calculated that the length of the vector v is equal to the square root of 10. I'll now substitute these values into the equation for the angle between two vectors. The dot product, u dot v, is equal to 10. The length of the vector u is equal to the square root of 20. And the length of the vector v is equal to the square root of 10. When we calculate the arc cosine of this value, highlighted in red, we get an angle of 45 degrees, or 0.79 radians. So we've calculated that the angle theta between the vectors u and v shown to the right is 45 degrees, or 0.79 radians. I'll now describe how to test whether two vectors are perpendicular. Two non-zero vectors are perpendicular if the angle between them is 90 degrees. We can determine this by calculating the dot product of the two vectors. Two vectors u and v are perpendicular if and only if u dot v is equal to 0. To explain this, the cosine of 90 degrees is equal to 0, and the arc cosine of 0 is equal to 90 degrees. The arc cosine is another name for the inverse cosine function. The angle theta between two vectors u and v is equal to the arc cosine of u dot v divided by the length of the vector u multiplied by the length of the vector v. Because the arc cosine of 0 is equal to 90 degrees, the angle theta between u and v will be equal to 90 degrees when this value highlighted in red is equal to 0. This value will be equal to 0 when the dot product u dot v is equal to 0. So we have the two vectors u and v are perpendicular if and only if u dot v is equal to 0. I'll now demonstrate this test with an example. For the vector u equals 3 minus 1 and the vector v equals 2, 6, u dot v is equal to u1 v1 plus u2 v2. For this example, u1 is equal to 3, v1 is equal to 2, u2 is equal to minus 1, and v2 is equal to 6. 3 multiplied by 2 is 6, minus 1 multiplied by 6 is minus 6, and 6 minus 6 is equal to 0. Because the dot product of u and v equals 0, this means that these vectors are perpendicular. The dot product has the following properties. If u, v, and w are any vectors and c is a scalar, then u dot v is equal to v dot u. cu dot v is equal to u dot cv, and this is equal to c multiplied by the result of u dot v. The dot product of u and the result of v plus w is equal to u dot v plus u dot w. U dot u is equal to the length of u squared. And the dot product of the 0 vector and u is equal to 0. I'll end this video by deriving the equation for the angle between two non-zero vectors. We start with the parallelogram law of addition of vectors. For two vectors u and v in standard position with initial points at the origin, the resultant vector u plus v is the diagonal of the parallelogram, which can be created from the vector u and the vector v, with the vector u plus v's initial point also being the origin. For the vector v and a vector w, the resultant vector v plus w is equal to the vector u, where the vector u is the diagonal of the parallelogram, which can be created from the vector v and the vector w. So we have that v plus w is equal to u. Moving v to the other side of the equal sign, we have the vector w is equal to u minus v. When we write the vector w is equal to u minus v, we mean that the vector w is equal to the vector u plus the vector minus v. The vector minus v has the same length as the vector v, but it has the opposite direction. We can add the vector u plus the vector minus v by placing the initial point of minus v at the terminal point of u. This is now shown to the right. So we have that the vector w is equal to u minus v. We represent vectors with arrows, which we refer to as directed line segments. Directed line segments with the same length and direction are treated as being equivalent. We can equally represent the vector w with a directed line segment with the same length and direction, whose initial point is at the terminal point of the vector v. The vectors u, v, and w shown to the right form a triangle. We can apply the law of cosines to this triangle. For the angle theta between the vectors u and v, the length of the vector w squared is equal to the length of the vector u squared plus the length of the vector v squared minus 2 times the length of the vector u times the length of the vector v times cos theta. When we move these terms, highlighted in red, to the left-hand side of the equal sign, and the length of the vector w squared to the right-hand side of the equal sign, we get that 2 times the length of the vector u times the length of the vector v times cos theta is equal to the length of the vector u squared plus the length of the vector v squared minus the length of the vector w squared. The length of the vector u squared is equal to open bracket the square root of u1 squared plus u2 squared, a close bracket squared. The square and the square root cancel each other out, giving us u1 squared plus u2 squared. The length of the vector v squared is equal to open bracket the square root of v1 squared plus v2 squared, a close bracket squared. The square and the square root cancel each other out, giving us v1 squared plus v2 squared. For the length of the vector w squared, because the vector w is equal to u minus v, we can express the components of the vector w in terms of the components of u and v. The components of the vector w are equal to u1 minus v1, u2 minus v2. Using these components for the length of the vector w squared, we get open bracket the square root of u1 minus v1 squared plus u2 minus v2 squared, a close bracket squared. The square and the square root cancel each other out, giving us u1 minus v1 squared plus u2 minus v2 squared. When we square u1 minus v1 and we square u2 minus v2, we get u1 squared minus 2 u1 v1 plus v1 squared plus u2 squared minus 2 u2 v2 plus v2 squared. We can now express the length of the vector u squared plus the length of the vector v squared minus the length of the vector w squared in terms of the components highlighted in red below. When we do this, these components highlighted in red cancel each other out. Because of this, the length of the vector u squared plus the length of the vector v squared minus the length of the vector w squared is equal to 2 u1 v1 plus 2 u2 v2. We can express 2 u1 v1 plus 2 u2 v2 as 2 multiplied by open bracket u1 v1 plus u2 v2 close bracket. Returning to our equation at the top of the screen, highlighted in red, because the length of the vector u squared plus the length of the vector v squared minus the length of the vector w squared is equal to 2 multiplied by open bracket u1 v1 plus u2 v2 close bracket, we can now express 2 times the length of the vector u times the length of the vector v times cos theta as being equal to 2 times open bracket u1 v1 plus u2 v2 close bracket. So we have that 2 times the length of the vector u times the length of the vector v times cos theta is equal to 2 times open bracket u1 v1 plus u2 v2 close bracket. Dividing by 2 on both sides of the equal sign, we get the length of the vector u times the length of the vector v times cos theta is equal to u1 v1 plus u2 v2. If we divide on both sides of the equal sign by these terms highlighted in red, we get that cos theta is equal to u1 v1 plus u2 v2 divided by the length of the vector u multiplied by the length of the vector v. Because cos theta is equal to this value highlighted in red, the angle theta is equal to the arc cosine of u1 v1 plus u2 v2 divided by the length of the vector u multiplied by the length of the vector v. u1 v1 plus u2 v2 is the dot product of the vector u and the vector v. So we can rewrite this equation to be the angle theta is equal to the arc cosine of u dot v divided by the length of the vector u multiplied by the length of the vector v. So we've just derived the equation for the angle between two non-zero vectors. To summarize, in this video we've learned about the dot product. We've learned how to calculate the angle between two non-zero vectors, and that the dot product is a key part of this calculation. We've also learned how to test whether two vectors are perpendicular by calculating the dot product of those two vectors. If you found this content useful, please subscribe to the channel to receive more content. Thank you very much for watching this video. See you next video.